Question 19. So this is quite a lot of inorganic chemistry actually. So this is period 3 chemistry. We're talking about the oxides of period 3 elements. They both react with water. So these period 3 oxides, they both react with water. So the one which is insoluble in water, that means Al2O3, SiO2, insoluble in water. As a result of them being insoluble in water, their pH is just pH 7 in water because they are insoluble. Alright, so that means Al2O3 and SiO2 is definitely out. So option A is out. Option B is out because it says both of them react with water. And option D is out because it has got SiO2 as well, which is insoluble in water. So guess what? You're just left with option C, which is Na2O as well as P4O10. This is your basic oxide, that is the property given, and this is your acidic oxide, as also the property given. One of them is alkaline or basic oxide, one of them is acidic. In the theory paper, you've got to know how to write equations, how to write balance equations. So make sure that what I'm doing here helps you in the long run. So this is phosphorus plus 5, because you can get 4 phosphorus plus 10 times minus 2, giving you the overall oxidation state of the compound is 0. So phosphorus is plus 20 over 4, phosphorus is plus 5. We are not doing a redox, they are just dissolving in water to give you the acid, because this is an acidic oxide. So the acid that you're going to get will be phosphorus plus 5, which is PO4 3 minus. That's why it's H3PO4 and not H3PO3, because this is the phosphate. This is phosphate and not phosphite. Okay, so this is PO3 3 minus, that is phosphite. So phosphate, phosphite, sulfate, sulfite. So these are all common naming exercises. Whatever you write, you have to balance it. 4 phosphorus, so 4 phosphorus. And then 12 hydrogen, so 6 H2O, and then 6 oxygen and 10 oxygen, so 16 oxygen, just like that. That is how to show that is a basic oxide, because it dissolves in water to give you an alkaline solution. Acidic oxide dissolves in water to give you an acidic solution. However, not every acidic oxide is soluble in water. SiO2 is actually acidic, but then it's insoluble in water. Okay, so SiO2 is acidic oxide. You can refer back to your O level. So when you have calcium oxide as well as SiO2, this gives you calcium silicate. Imagine that calcium 2 plus, SiO3 2 minus, this is calcium silicate, and this is slag, and this is in the extraction of iron in the blast furnace. When you use limestone as one of your starting materials, decompose to calcium oxide, and then you want to remove the acidic impurities such as SiO2, they will react with the calcium oxide and give you slag, which will be separated off from your iron, okay, which you can extract after that from the molten bit. Question 20. So we are starting to move towards organic chemistry now. This says stereoisomerism. You need to be very careful about the terminology used, because stereoisomerism can be divided into two, which is optical isomer. So that's to do with the chiral carbon, and there can also be the geometric isomer, which is to do with the cis and trans isomers. Okay, so for each of these, you should really write them out. So there's 2-methyl but-2-ene. So for that, we are going to draw from that. So there's 4 carbons. There's an alkene, carbon-carbon double bond. And there's a branching. So there's a CH3 branching. And it's at position 2. So I will draw skeletal because I'm a big fan of skeletal. Okay. So 1, 2, 3, and 4 for the but. And then at position 2, I have that. I have drawn a trans where these 1 and 4 are on the opposite side. Doesn't matter, we'll worry about the cis and trans later on. I've got a methyl at position 2, so I've got a methyl at position 2. And once I've drawn in the methyl at position 2, I can see that these two groups are exactly the same. When I have two groups that are the same on the same carbon of the carbon-carbon double bond, I no longer have cis and trans. and I no longer have geometric isomerism essentially, because one of the criteria to have geometric isomerism is to have different groups on the same carbons of the carbon-carbon double bond. That's the second condition that a lot of students doesn't know about, or are not very aware about. Not just carbon-carbon double bond, but you must have different groups or different atoms on the same carbon of the carbon-carbon double bond. So A does not show stereoisomerism because there's no chiral carbon here to begin with as well. So let me go through B. What do I have in B? I have 2-chloro-propan-1-ol. So I have propan-1-ol. So 1, 2, and 3. I have 2-chloro. What I can see is I have a chiral carbon because this carbon is bonded to 1, 2, 3, and there's a hydrogen, 4 different groups. But then there is no cis and trans. However, they just say stereoisomerism, so it could be this, or it could be this and this. Okay, so it's not necessarily just saying that both optical and geometric. They just say stereoisomerism. There's a chiral carbon there, a carbon bonded to 4 different groups. There is 1 hydrogen which is not shown because it's a skeletal formula that I have drawn. I think B is the answer. Let me just quickly go through the other options. Difluorochlorobromomethane. So you have a methane, and then you have difluoro, and then you have chloro and bromo. Okay, so obviously these are the same, and therefore you have no chiral center. Okay, so it's not optically active. There are no optical isomers. Pent 1 int 1, 2, 3, 4, 5. Well, here you have CH2 double bond. You have 2 atoms or 2 groups that are the same. On the same carbon of the carbon-carbon double bond. So therefore, no geometric isomerism. My handwriting is getting really bad, isn't it? No geometric isomerism or no cis-trans isomerism. So again, I stand by my earlier choices, which was B. Okay. Question 21. So what do we have here? We have 2 carbon-containing products. So there's alkene Z with a hot concentrated acidified KMnO4. So there's H plus MnO4 minus. So that is to do with extreme conditions. And these extreme conditions under hot and concentrated KMnO4 acidified is going to lead you to the oxidative rupture or oxidative cleavage or oxidative rupture of the carbon-carbon double bond. And they say the products give an orange PPT with 2,4-dehane pH, and 2,4-dehane pH is a test for aldehyde or ketone. Okay, aldehyde or ketone, it could be N as well. The other product is a gas. Okay, it's a gas that give a white precipitate with aqueous calcium hydroxide. Aqueous calcium hydroxide saturated, meaning the maximum amount that can dissolve, is what you call lime water, in case you never know about it. So calcium hydroxide is used to test as a lime water, is used to test for carbon dioxide, and that will give you an insoluble precipitate, because that is just your group 2 chemistry that even year 9, year 10 student would know. And they will give you H2O because this is acting as an acidic oxide, and it is acting as a base and alkali, and you get a salt and you get water. And what happened is this is insoluble because it's a group 2 carbonate. They don't like to dissolve. You get a white precipitate, which means one of the gas you produce is going to be this carbon dioxide. Carbon dioxide gas is produced from this oxidative rupture of the carbon-carbon double bond if we have a CH2 double bond. So that's one of our hint there, all right? Whereas the aldehyde or ketone could be a RCH double bond. But that will give a carboxylic acid, so it cannot be RCH. It has to be R dash like that, which will not give you an aldehyde. It will give you a ketone, all right? And because the aldehyde will be further oxidized to carboxylic acid, and carboxylic acid will not give you orange beauty with 2,4-dehane pH. There you go. I identified the 2 fragments of the alkene. Then we just go through our options, which is whatever is given. But 2 int, so it could be cis, it could be trans, or it could be cis. Doesn't matter, because when we look at it, we have no CH2 double bond, therefore we don't get any CO2. I can't even erase that properly. Therefore, no CO2, therefore it's wrong. Okay. Let's have a look at B. We have 2-methyl-propene. So this is 2-methyl-propene, 1, 2, and 3. You have propene, you have 2-methyl-propene. When I break that, I can see that I have a CH2. So this is a CH2 double bond that will give me CO2. I also have, better use a different color. I also have this thing here, which will give me a ketone because this is a RCR- carbon double bond. It will give me a ketone. I think B is our answer. But then let's just go through the other options and just to make sure that I have not done any mistake since I'm not doing this in the exam condition, so I don't really have to worry about time pressure at all. But obviously in the real exam, you have to worry more about that. Okay, so just like the previous questions, there is that, but then there is no CH2 double bond, so no CO2, therefore C is out. And propene, well, this side will give you CO2 because you have a CH2 double bond. However, what happened on this side is you have a RCH double bond that will give you a carboxylic acid, and that will not react with DNPH because carboxylic acid don't give you orange PPT with 2,4 DNPH. So again, D is wrong, which means B is the only acceptable correct answer. Question 22. So this is a mechanism question, and this is asking about HBr to ethene. So without looking at the mechanism first of all, we can hopefully see that if we have to do from scratch, okay, I'm just showing you what I will do from scratch. First thing is dipoles. So delta plus on the hydrogen, delta minus on the electronegative bromine. Then the rich in electron, rich attack poor, as you can see from all my topical playlists on the mechanisms as well as the AS topics. This thing here goes to the hydrogen and then break that Br. So what happened now is you no longer have a carbon-carbon double bond, you have a carbon-carbon single bond. Hang on, I'll just put in the H here and I have a plus there. But I could also put the H on the other side and then I have a plus there. This is what I call carbocations. The carbon with a positive charge is bonded to one other carbon. The carbon with a positive charge is bonded to one other carbon. Both of them are carbocations. And carbocation is an intermediate, meaning to say you will get a double harm in the reaction profile diagram. However, what is important is these two intermediate, despite, well, irrespective of where I put the H, and I will end up with the same carbocations, so they are the same thing. So I'll just work on one of them. They're not always the same. When your alkene is unsymmetrical, then it will not be the same carbocation. Be very careful, yeah. You have kicked out both the electrons to the bromine. So what you have is you have bromide, okay, with the lone pair that will attack the carbon. I can't even get this right. They will attack the carbon with the positive charge. It does not attack the positive charge because it's the rich in electron from the lone pair. Attack the atom. Okay, the positive charge is on the carbon actually, so it doesn't attack the positive charge. It attacks the carbon because it wants to form a carbon-bromine bond. So this is your classic electrophilic addition mechanism. If you look at your products, so it really does not matter where I put the bromine, could be here, here, or here, because this molecule can rotate around about the single bond. What is important is you get a carbocation intermediate. Okay, so all of them are carbocation intermediate. We attack from the rich to the poor, which means here also rich to the poor. From here, you can see option A is definitely wrong, and option D is definitely wrong. And then from here, you're left with B and C. You can hopefully see from the rich to the poor. So the rich is this bit because you have kicked out rich attack poor. You have kicked out the Br minus. So rich attack poor. So that has got to be option B, which is the correct answer. Okay, which means, well, option C is definitely incorrect because you kick out a hydride, which is H minus. That is not going to happen based on the initial electronegativity difference. Question 23, what do we have here? This is about SN1 versus SN2. So we know that SN1 is a two-step mechanism. So some students always think that the one means in one step. Nope, it's a two-step mechanism. It is via a carbocation intermediate. So this term intermediate was the same as what I've talked about in the previous questions. So what we are saying is, I don't know about the enthalpy change of the reactions, but I'm just speculating here. But what I know is I have a intermediate, okay, intermediate, and what I have is your reactant and your product. This is going to be progress of reactions, and this is going to be energy profile diagram for a reaction involving a intermediate, a double harm reaction profile diagram. Then what in the world is this number one then? Okay, this will make more sense in the A2 rate of reaction topic. This is actually first order overall, okay, and this means that there is only one reactant in the rate determining step, which is the slowest step in the reaction. This is called rate determining step. It's not in the AS syllabus unless you're doing a different A-level syllabus. However, you definitely learn about this in the 9701 A2 syllabus. So when we look at it, you can imagine that this thing here, which is a carbocation intermediate, a tertiary carbocation is going to be more stable than secondary carbocation, more stable than primary carbocation, because of what you have learned in the electrophilic addition mechanism as part of alkene chemistry. These are more stabilized due to more alkyl electron donating groups by inductive effect. These are all stated in the alkene topic before you even reach this topic on SN1 or SN2. So giving you an example, this is a tertiary halogen alkane, giving you a tertiary carbocation, a secondary halogen alkane giving you a secondary carbocation, and a primary carbocation coming from the primary halogen alkane. You have electron donating groups, you have three of them. Donating electrons to an electron deficient center is stabilizing by inductive effect, and therefore it's more stable compared to secondary, compared to primary. So our job really is to look for tertiary halogen alkane, both of them via SN1, both of them via SN1. Which pair of halogen alkane both react? Oh, okay, it's going to be option A, because you can see that you have got a halogen alkane there, which is tertiary, as well as the chlorine one. The carbon with the halogen is bonded to, so the red carbon, the carbon with the halogen is bonded to 1, 2, and 3 other carbon. The carbon with the halogen is bonded to 3 other carbons. That is going to be your tertiary halogen alkane. Let me just give you an example of what I talked about in terms of the rate determining step just now. In an SN1 mechanism, the first step is the rate determining step. This is the slow step. On its own, there's only one molecule involved. The nucleophile, it does not get involved in the first reaction. They just break the carbon-bromine bond. You get a carbocation intermediate, and then kick out the Br minus. What happened in the second step is your carbocation intermediate get attacked by the electrophile, by the nucleophile, I beg your pardon. So this is going to be the fast step because there is no longer the rate determining step. And then there's that. In your overall equation is not a mechanism. Your overall equation is just like a balance equation. So what happened there is they just give you the nucleophilic substitutions, or you can just imagine the type of reaction is substitution, but the mechanism is nucleophilic substitution, SN1. Okay. Question 24. So what do we have here? Looks a bit complicated. Combustion, but you have a mixture. This is what is complicated about it. You have a mixture. Okay, I think I can understand this question. Careful with it. It's not your usual balancing equation, because if you look at that, there is 120 degrees Celsius. That is not room temperature and pressure. So we cannot use molar volume of gas, which is equal to 24 dN³ per mole. This is at room temperature and pressure. That is at 25 degrees Celsius or 298 Kelvin. This seems more like an ideal gas question actually. it is an ideal gas question, and then at 120 degrees Celsius, I think H2O is going to be a gas. It's a gas because it already boils at 100 degrees Celsius, right? So H2O is a gas, so we have to consider the volume of the gas as well. CO2 is a gas as well already, even at room temperature. So what do we have? We have the total volume of gas. Is this sensible? Is this any good? Let me think. Is this going to be ideal gas question or not? Maybe not. It's probably less complicated than this. Okay. So whatever new molar volume of gas does not matter, because we know that for gases at this new temperature, the volume ratio of gas is going to be equal to the mole ratio of gas. It's just the fixed number, which is the molar volume of gas, that will change, but the volume ratio and the mole ratio is still the same. So I don't think I need to worry too much about that. What I'll do is I'll write a balance equation. That's probably the first thing I will need to do for this question. So C2H5OH plus O2 giving me CO2 and H2O, complete combustion, 2 carbons, so 2 carbon dioxide, 6 hydrogen, so 3 H2O, and 4 oxygens plus 3 oxygen, 7 oxygen, minus 1 oxygen. I need 6 oxygen, so I need 3 O2 there. When I have methanol will give me 1 CO2 and will give me 2 H2O, because I've got 4 hydrogens, 2 oxygens, plus 2 is 4 oxygen, minus 1, I need 3 over 2 here. If I then just add the two equations together, so C2H5OH, ethanol, plus the methanol, I would need 3 plus 1.5, so there's 4.5, there's 9 over 2 O2, I think, so 6 over 2, yep, okay. And then I'll get 3 CO2 plus 5 H2O. At 120 degrees Celsius, H2O is a gas. Okay, carefully, it's a gas. So what do I know? I know this is 35 cm cubed, and I know this is 55 cm cubed. So I just don't know what is the molar volume. I just don't know what's the ratio of these and these there. Okay, this is assuming it's 1 and 1. How about when it's not 1 and 1? This is assuming, hang on, let me see, assuming 1 to 1, but we know that it might not be 1 to 1, right? What can I do? What's the best way to address this question? Yeah. Okay, let me say there's A mole, and then this will be 2A, and then there will be 5 plus 1 is 6 hydrogen, so 6A, so I will have 3A. Okay, and then if I have B here, that means I'll have B CO2, and I'll have 4 hydrogen 4B, so I have 2B, so I have 2B, like that. Okay, so assuming I have all that, so I should have, instead of 3 and that, I should have 2A plus B, I should have 3A plus 2B, I should have A, and I should have B. Okay, now I'm no longer assuming. Now I can do my ratio, I think, because 35 cm cubed to 55 cm cubed, if you divide by 5, what do you get? You get 7 and you get 11. So what we are saying is 2A plus B is equal to 7, and then 3A plus 2B is equal to 11. Okay, so we are given options. I don't even want to solve the simultaneous equations, because A is the ethanol, A is ethanol, so this is the ratio of ethanol is to methanol. A is to B, right? So based on the option given, just try the option given. So 1 is to 3. Let's check. 2 times 1 plus 3, that gives me 5. So that is wrong, because 2A plus B should give me 7. And then B, 2 is to 3, so 2 times 2 plus 3, well, they give me 7, that is fine. Let me just double check the second one. So 3 times 2 plus 2 times 3, so 6 plus 6 give me 12. So I don't think this is right because it doesn't satisfy the second simultaneous equations. That is for the water, sorry, not water, for the steam, because it's a gas at 120 degrees Celsius. Okay, I might have to play around with space a bit more. Let me just move that up a little bit so that I can check through the rest of the option. Yeah, let's go through C. So what do we have in C? 3 is to 2. So if I check 2a, so 2 times 3 plus 2, so that is 8. That is not making any sense at all. So C is wrong, which means D is most likely the correct answer. But let's just double check because we can never be sure, right? So 2 times 3 plus 1 is 7, so that is okay. 3 times 3 plus 2 times 1, that is going to be 11. There you go. We have just solved it. All right, so the answer there must be D. I haven't solved the simultaneous equation. I could. I mean, you could, but rather than going through that, why don't I just, use the answer given? What is most important, I guess, is at 120 degrees Celsius, you get a gas. You get a different molar volume of a gas because you are no longer under room temperature and pressure. However, what is important is the volume ratio of gas. That will give you the mole ratio of gas. Balancing equation is alright, but most people forget that there's for 1 mole and 1 mole. And your job here really is you have a mixture. So we're just dealing with algebra. So not too tricky at all, I think. Question 25. So what do we have here? We have reactions of ethanol. So we have ethanol, 2 carbon alcohol. So we're doing oxidations with the dichromate 6 acidified, and we get ethanol. So we got to heat and distill immediately because we want to get the aldehyde that has a lower boiling point as it doesn't form hydrogen bonds with each other. Whereas if you want to go to the carboxylic acid, you will just reflux it all the way. And then the second one is ethanol plus sodium metal, and you get alkoxide, and this will give you hydrogen gas. But because you only have one hydroxyl there, only one of the hydrogens give you the hydrogen gas, so there's half mole of that. This is actually redox reaction. If you think about it, sodium 0, sodium plus 1. Hydrogen in a compound, hydrogen plus 1. Hydrogen as a molecule, bonded with itself as an element, hydrogen 0. This, on the other hand, is an oxidation reaction. You are using this as an oxidizing agent to oxidize the alcohol. The carbon with the OH, you started with 2 hydrogens. Now you ended up with 1 hydrogen only. Only left 1 hydrogen. So just now you have 2 hydrogen. Okay. Which statement about this reaction is correct? The formation of both ethanol and sodium ethoxide are redox. Well, this is not. Actually, that is correct because this is oxidation. But just because this undergo oxidation, don't forget the Cr2O7 2 minus. This is chromium plus 6. This is orange. That will undergo reduction. You go to chromium 3 plus, which is chromium plus 3 aqueous solution, and that is actually green. So even though I put down oxidation there, but you know that it happens together in tandem, together with reductions. There's redox reactions. So option A is what we are looking for there. Okay. Option B, they say result in color changes. We are not going to see big color changes here at all because there's no transition metal compound involved at all whatsoever. And they say the formation of ethanol has to be catalyzed. Not really. This is acting as a reactant because it gets reduced. It doesn't go back to this in the end. And they say D is a dehydration. You don't kick out any water. You kick out H2 gas. All right. Okay. Question 20.